All right, asynchronous, week 6. Here we go. We started out, or we left off last time, sketching 2 different rational functions. In both cases, we ended up in a situation where the degrees in the numerator and denominator were the same. In both situations, we had horizontal asymptotes. Let's see what else. We had vertical asymptote in one, no vertical asymptotes in the other. So I want to go over 2 more rational functions. One of them is going to be a little bit more like the first 2 that you saw. And then the other one is going to have something called a slant asymptote in it. I thought about skipping this, but it's something you actually learned in college algebra, so you have seen it before, and I already assigned it for number 13, so now I kind of have to talk about it. I was like, did I already do that? Yes, okay, fine. Then I want to go over 2 polynomials and 1 radical, and that's it. And then you will have seen what I have to show you with curve sketching. So without further ado, example 3. All right, so here we go. Example 3, f of x equals 4x divided by x squared minus 4. Okay, so remember we have a list of things that we're looking for here, and the first thing we're going to do is find the domain. So remember that what we're looking for the domain are values that are going to make the denominator 0. And I feel like we're pretty comfortable with looking at these functions at this point. Most of you guys are going to be able to eyeball this and not have to actually solve this equation. But you're looking for values such that x squared cannot be equal to 4, and then x itself, then if you take the square root on both sides, cannot be equal to plus or minus 2. So clearly if x is 2 or negative 2, you're going to end up getting 4 minus 4 in the denominator, which is no good. Now I want you to remember these values because every time you take your derivative, this denominator is going to just continue to show up in each derivative. So when that happens, I want you to know that plus or minus 2 cannot be a critical number because it's not in the domain of your function, and plus or minus 2 can't possibly be a point of inflection because it's not in the domain of your function. It could be that the concavity changes at the vertical asymptote, but it can't technically be considered a point of inflection. Okay, so we have the domain. The next thing we're going to do is look for intercepts, which will end up giving us some nice points on the graph. As far as our intercepts are concerned, we'll look for an x-intercept first. Remember to find the x-intercept, we let y equals 0. That means f of x equals 0. So we're going to take our function and set it equal to 0. Now remember that in order for a rational expression to be equal to 0, we just need the numerator to be equal to 0. And in this case, that means x equals 0. If x equals 0, f of 0 then is also 0. So you end up with an x-intercept at 0, 0. So who knows? That might be useful to us. Maybe not. We'll see. But it's x and then, oh, sorry. Yeah, of course we had 0 there. Whenever y equals 0, x equals 0 in this case. So that's why we have this point 0, 0. For your y-intercept, we're going to let x be 0. To find the y-intercept, let x be 0. That means we're finding f of 0. F of 0 is 4 times 0 divided by 0 squared minus 4, which is 0, over negative 4, which is 0. So again, you're just getting this point 0, 0. So not too exciting. Sometimes you'll get some good information there. Other times, nothing too exciting. That's okay. The next thing we'll look for is asymptotes. To find your asymptotes, we're looking for these places where you have these infinite discontinuities. Again, just take a look over here at your function. We excluded plus or minus 2 from the domain. In our case, there's no way that you could cancel out either of these to be removable discontinuities. You don't have a factor of x plus 2 or x minus 2 in the numerator that would cancel those out. So both of those discontinuities are infinite. So for sure, we know that we have vertical asymptotes at x equals -2 and x equals +2. So this is going to really shape our graph. So it's really important that we call those out. As far as the horizontal asymptote is concerned, remember that we have rules for these. You can always go through that process of finding the limit as x approaches plus or minus infinity. But remember I showed you a trick for this? If you don't remember the trick, that's fine. We do have rules, and you are allowed to use notes on the test. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. But if you remember the trick, what we did is we rewrote f of x so that it would have the same degree in both the numerator and the denominator. So just creating that term that wasn't actually there. So our original function just had 4x in the numerator and x squared minus 4 in the denominator. When we do this, we can use that rule that says that if the degree in the numerator is the same as the degree in the denominator, that y just equals the ratio of the lead coefficients, which in this case would be 0/1, and y equals 0. So whether you obtain your result this way or by using that rule that states that if the degree in the numerator is less than the degree in the denominator, your horizontal asymptote is y equals 0, does not matter to me. Either way, you have a horizontal asymptote at y equals 0. So that's something. Okay, that's the algebra part. Now we get to the calculus part. This is why we do what we do. F prime g minus f g prime. We're going to use the, actually we don't need the chain rule there. Sorry, I'm getting ahead of myself here. F prime g minus f g prime, there's no power on that, divided by g squared. This is 4x squared minus 16 minus 8x squared divided by x squared minus 4 quantity squared. This will end up giving you negative 4x squared minus 16 divided by x squared minus 4 quantity squared. Now, if you're thinking that you might want to try to factor something out and cancel, be careful here, because I know it looks like you might be able to cancel a common factor, but you actually aren't able to, because you would have to factor out a -4. And when you did that, negative 16 divided by -4 would give you +4. So even though you will probably use this later, you might just want to leave f prime unfactored just for purposes of taking your second derivative. But notice that you can't cancel anything out here because you have x squared minus 4 and x squared plus 4, which are not the same factor. So if you're thinking like, oh, it must have been meant to be, I must have done something wrong, it is what it is. All right, let's take f double prime. So f prime is negative 8x times g minus f. And then g prime is where we need the chain rule. So bring down your exponent, rewrite the inside function, take it to the first power, and multiply by the derivative of the inside function. And then divide that by g squared. When you square the square, you get to the 4th power. And again, I'm checking this again because you just never know when something could go wrong. So f prime g minus f g prime. All right, looks good to me. And then we'll simplify. I'm already just grabbing my calculator because I'm prepared for having to use it here. All right. Remember when you're taking the second derivative with the quotient rule, a lot of times you end up being able to cancel out this common factor that is currently residing in the denominator and in each one of these terms. So take out one factor of x squared minus 4, and that'll make your life a little bit easier. Now you can distribute because you just have the first power here. So we'll take negative 8x cubed plus 32x. And then I can just go ahead and multiply through here. And I'm going to be careful because I have this minus sign. There's a lot going on here. So if you would like, even do this in 2 steps, that's fine. Technically, I'm taking 4x and I'm multiplying it by this quantity in here. And then I'm also multiplying it by the negative sign. So this is going to be negative 4x times negative 4x squared, which is going to be positive 16x cubed. And then you're taking that same negative 4x and multiplying it by positive 16. So negative 4x times positive 16 will end up giving you negative 64x. And then we'll divide by, let's see, our denominator. And again, just checking here to make sure that everything looks good. Let's see. Positive 64x. I think I said positive and wrote negative. I don't know. A negative times a negative gives you a positive, and the 2 and the 2 are positive. So that gives you a positive 64x. But everything else looks good. Okay. And then we'll simplify. So we'll have positive 8x cubed and then plus 96x divided by x squared minus 4 quantity cubed. And there's f double prime. It'll be easier for you to put that into your calculator if it's in this form. We're going to look for possible points of inflection anyway, and you're going to factor it then. So you might as well just let it be for right now. All right, so we have f prime and f double prime. We should be pretty good with taking those derivatives. Now we're going to look for critical numbers and possible points of inflection. So I'm looking right now at places where f prime of x equals 0, and that's going to occur when I have negative 4x squared minus 16 equals 0. So taking that numerator and setting it equal to 0. So I'll have negative, well, I guess I'll add 4x squared on both sides. And then that leaves me with positive 4x squared equals negative 16. Well, look at what happens then. You get x squared equals negative 4. Cannot be. And then remember that when you are looking at your denominator for values where f prime cannot possibly exist, well, that's going to occur at x equals plus or minus 2, but these values are not in the domain of f. So if you're thinking like, this seems wrong, I don't know, this doesn't seem like a good idea to me, there must be something wrong if I have no critical numbers. It happens sometimes. We have no critical numbers. We have no values that make the numerator 0, and we have no values in the domain that make the denominator 0. And this means that on our graph, we're going to have no local extrema. Such is life. So unfortunately, we're not going to be able to glean much information as far as that's concerned, but that's okay. We have a lot of asymptotes, so we have some good info. Next, we're going to take f double prime of x and set it equal to 0 to look for some possible points of inflection. And that's going to be when 8x cubed plus 96x equals 0. 8 is a common factor. X is a common factor. That will leave you with x squared plus 12 equals 0. that means 8x equals 0, or x squared equals negative 12. X squared cannot equal negative 12. But it's possible that your numerator can equal 0 if x equals 0. So this is the only point of inflection you're going to get. Note that f prime of x does not exist at x equals plus or minus 2, and these are not in the domain of f. They're vertical asymptotes, so they're not going to represent any sort of local extrema. They're not going to represent any sort of points of inflection. Now, we actually already obtained a value at x equals 0 because it came from our intercept. So again, not that exciting, but if you're thinking about this as a point of inflection, well, we'll get it out of the chart actually. So I'm just going to highlight this for right now as a possible point of inflection, and then we'll get the corresponding y value in the chart because we need to get good with that anyway. Okay. Once we've gotten that done, we're going to go through and make our chart. I'm going to pick out all the important pieces. So I know we keep saying that, okay, plus or minus 2 can't be local extrema, can't be points of inflection. However, because they represent vertical asymptotes and there could be changes on either side, those values have to go in the chart. The other value that has to go in the chart is x equals 0. We don't have any critical numbers, so we don't have anything else. We're just going to have 0 and plus or minus 2 as the values that go into the chart. So I'm going to start out at the lowest value in my domain. I'm going to leave a little bit of room here so I can label some things. I'm going to go up to negative 2, and then I'm going to just pause at negative 2 so I can actually just state what it is. I'm going to go from negative 2 to 0, 0 to 2, and then 2 to infinity. I'm going to look at f of x, f prime of x. Okay, I know sometimes we say f prime of the test point, but I'll just simplify it to just f prime of x, and we'll just let x be whatever value at which we're evaluating the function. And then we're going to make our conclusions. Okay. There it is. I'm going to test some values you probably would have expected. 1, 3, negative 1, negative 3. Now, remember that negative 2 and positive 2 are excluded from the domain. For all of these values, they're going to be undefined. So you're going to get an error in your calculator if you try to evaluate them here. It's undefined in every place. So if you want to fill that out, you can. And we can always go ahead and make the conclusion that it's a vertical asymptote just so that we remember what it's doing, what we're doing with that. So I'm going to go ahead and enter f of x in my calculator. I had to play around with my lighting a lot tonight because I'm using pencil because I cannot do curve sketching in pen. So yeah, it's about what I expected would happen. I don't know, you guys. All right. We know how to enter these functions in our calculator. Let me see. I'm going to enter them, and then I'll see if I can sort of do a shift so that you can see them. 4x divided by x squared minus 4 in parentheses. My first derivative is parenthesis negative 4x squared minus 16, close your parenthesis, divided by the quantity x squared minus 4 to the second power. And then my second derivative is 8x cubed in parentheses plus 96x, close your parenthesis, divided by x squared minus 4, close your parenthesis, to the third power. Let's see. Can we see that? Kind of. Sheesh. I need to get on the school to pay for my my subscription to the TI emulator, which is also a pain because I have to keep unsharing my screen and sharing the emulator. It's just not ideal. Okay, but anyway, this is what I've got. Maybe it just seems like if I angle it, sometimes it's better. This is like worse than I've ever seen it. Just wow. Okay. You should be pretty good at this by now. So I'm going to go ahead and write down what's in my table. If your values don't match, then you'll know you entered something incorrectly. Remember, y sub 1 is your f of x. I'm using -3. I'm not bothering with -2 because I already know it's going to be undefined. -1, 1, 3. And then if you just want to pop 0 in at the bottom, just so you can see what's happening at 0, that's fine. So y sub 1, I have -2.4. At -1, I have 1.3 repeating. At 1, I have -1.3 repeating. And at 3, I have 2.4. And then for y sub 2, I have -2.08, -2.2 repeating, -2.2 repeating, and -2.08. Interesting. My first derivative is negative everywhere. That must mean it is decreasing in every single interval. Okay, that's not necessarily a bad thing. It just is what it is. Y sub 3, I have -4.032, 3.8519, -3.852, and then 4.032. At 0, I have 0, -1, 0. Okay. I can go ahead and make some conclusions about concavity, negative, down, frown, positive, up, cup. Okay. So on my first interval, I am decreasing concave down. On the second interval, decreasing concave up. On the third interval, decreasing concave down. And on the fourth interval, we are decreasing concave up. Remember that x equals 0 represented a possible point of inflection. So that's kind of where we were expecting the concavity to change. And notice that on each side of this value at 0, your concavity is different. We went from concave up to concave down between these two intervals. So we can actually say that we have a point of inflection at 0, f of 0, which is the point 0, 0. So we're going to get that concavity change. So we'll be able to show that we go from being concave up to concave down. All right. That's your chart. Now we're going to make our graph. All right, I'm looking at the values that I have, trying to see exactly how I need to scale this out. Again, I have a situation where there's not a whole lot going on. I have asymptotes at ±2. I have a vertical asymptote at 0, but other than that, not much is happening. I have function values at -3, -2.4, and +3, 2.4, but nothing beyond that. So I might just go from -4 to +4 on both the x and the y axis. So I'm going to do that. I'm going to make this just bigger because I want us to be able to really see what's happening in our graph and be able to comfortably put our information down. So we'll do that. And then I'm going to go up to 4. I'm going to try to make this as square as possible. And out to -4, and I'll try to take the halfway point to get to 2. And the 2 is going to be really important on the x-axis because this is where we have our vertical asymptotes. Okay. So remember, we should be graphing our asymptotes first, and they will always be using dashed or dotted lines like that. So these are our vertical asymptotes. I also have a horizontal asymptote at y = 0. It's kind of hard to show an asymptote when it's lying on an axis. So if you want to sort of offset it a little bit just so I can see your dashes, that's fine. I also want you to see it when you're graphing so you don't forget that it's there. Do the best you can. I know I have a point at 0, 0. It's our x-intercept, it's our y-intercept, it's our point of inflection. There's a lot happening there. Other than that, I don't have a whole ton of information except that the graph is going to be decreasing everywhere, and I know something about its concavity. Okay, I can say that in this middle section, I can go ahead and graph something immediately. If you want to plot some points right away, you might find that to be helpful too. Looking at your chart, you know you have points at -3, -2.4. So maybe go ahead and graph that. So -3, -2.4. So if that's 3, that's about 2.4. You know, I'm just eyeballing it at a weird angle here. Yours will be much nicer, I'm sure. Okay, so that's our point at -3, -2.4. And then also I have another point sort of doing the same thing at +3, +2.4. So we're going to do the same thing up in this other quadrant. So let's see, +3, +2.4 is about right there. Something like that. Then we know that we have points at 1, -1.3, and -1, +1.3. So I'm going to graph those points also. That back there. -1, 1.3. It's about right there. And then +1, -1.3. It's right about there-ish. So that's helpful to us also. Okay, now we have information from the table. If you want to go ahead and graph this middle segment first, I think that'll be the easiest one to do. You know that from -2 to 0, you're decreasing concave up. And then from 0 to 2, you're decreasing concave down. The whole time you're decreasing, it's just that you go from concave up to concave down at the point of inflection at 0, 0. So we're going to be concave up on this left side interval and concave down on the right. And no matter what, we have to be approaching the vertical asymptote. So we're going to show this decreasing concave up cup, and then we're going to get this little flip where the concavity changes from concave up to concave down. We're going to go through that nice point we found, and we're going to approach the vertical asymptote. So that's the middle segment of the graph. Now, on the left and the right of the vertical asymptotes, we have, let's do the right-hand side first. Why not? It just seems like it makes more sense. That we are decreasing concave up from 2 to infinity. Okay, well, notice that you already have a point over here. To be decreasing concave up, the only thing we can do and go through this point is approach both of these asymptotes. Remember, we can cross a horizontal asymptote in the middle. It's just guiding the end behavior of the function as x gets very large or very small. So we're not going to be crossing the horizontal asymptote at the ends of the x-axis. Crossing it in the middle is fine because that doesn't control the end behavior. So in order to be decreasing concave up and go through this point, our function has to do something like that. And in order for us on the left-hand side, going back to our table, to be decreasing concave down, we're going to do something similar, except this time it's going to be over here in this piece of the graph. The only way for us to be concave down, frown, and decreasing as we go down from left to right is to, again, approach the vertical asymptote and approach the horizontal asymptote and still go through this point. And you can double check this in your calculator. It's already in there for f of x. If you would like, just go ahead and delete your other two graphs and double check and make sure that this is what your graph is supposed to look like. I just wanted to remind you that on the test, I'm going to be asking you to do your own problem like this by completing a chart. And I'm also going to be giving you an example where I give you a completed chart without the conclusions. So it would just be like, here's the test point, here's the function value, here are the values at f prime and f double prime, and then you would fill out the conclusions, and then you would graph the function based on this information. I would also be giving you any additional information such as x and y intercepts and asymptotes. So I would give you that as well. I want to make sure that you can interpret all this information and draw a graph from it. Okay. So that was example 3 with a rational function. I want to show you one more rational function, and I had mentioned the slant asymptote, and this one is going to have the slant asymptote in it. So this is example 4. F of x equals x plus 1 over x. Now, it's possible that you might see the function displayed to you like this. If you don't like the way it's written, you can always rewrite this using the LCD. So create an LCD here with x. So multiply by x over x, and then you can rewrite this as x squared plus 1 over x. And you might need to work your way back and forth. Like, for instance, when you take the derivative, you'll probably want to rewrite this such that you have, instead of x plus 1 over x, the easiest way to take your derivative would be x plus x to the negative first. So it kind of, you can play around working back and forth between these forms. All right, first thing we do is find the domain. So the domain of your function is any real number such that x cannot be equal to 0. In either case, you can see that 0 would make your denominator 0. So we're going to exclude 0 from the domain. So we have that. Intercepts. And then asymptotes. To find the x-intercept, let y equal 0. That means we let f of x equal 0. Use whatever form you like. Personally, I feel like it's easiest to use this form if you're setting a function equal to 0. That just means the numerator has to be equal to 0. And remember, that cannot happen in such a case. So you actually don't have any x-intercepts. This is the first time we've come across an example like that. So you would have no x-intercepts. And now you're wondering, what the heck is this function going to look like? How odd. It happens. With rational functions, Okay, no x-intercepts. So let's look for your y-intercept. Remember that occurs when x equals 0, which is f of 0, and use whatever form you like here. I don't know, maybe trying to find one that's like the least offensive form to use here. I don't know, I'm going to go again with this one. 0 squared plus 1 divided by 0 is 1 divided by 0, which does not exist. Therefore, you have no y-intercepts. And that's okay. You'll see this come together. Okay, so where the new piece of this comes in is with your asymptotes. For the vertical asymptote, well, that's no big deal. We already knew that we had an infinite discontinuity at 0. There's no way we can get rid of that discontinuity. It is what it is. So you have a vertical asymptote at x equals 0. Fine. And that makes sense anyway, since you have no y-intercept, it makes sense that you'd have a vertical asymptote on your y-axis. Okay, if you're looking for a horizontal asymptote, which you would do, remember I have the trick where you set the degree of the numerator to be the same as the degree of the denominator. Oh, not 0x squared. Oh yes, 0x squared. I just wanted to make room for that. 0x squared plus x. Okay, so it's gone now. Using this form, just equating these two and making a 0x squared in the denominator just to get those to be the same degree. And then the ratio of the lead coefficients, sorry, that was driving me crazy, is y equals 1 over 0, which would mean that your horizontal asymptote does not exist. Okay, so there's no horizontal asymptote, which you might be thinking is odd because maybe you thought that since there were no x-intercepts that there was probably a horizontal asymptote on the x-axis. But we do have a special case here. If the degree of the numerator of f of x is greater than the degree of the denominator by 1, we have a slant asymptote. I'm going to write that down. A slant asymptote, hopefully you saw this in college algebra or algebra 2, whichever you had, occurs when the degree of the numerator is 1 more than the degree of the denominator. And we have that situation here. Now, it would not have been easy to recognize given the way that I presented the function to you. So it's not obvious. You would have to actually rewrite it this way. But note that when you see it in this form, it's very obvious now that the degree of the numerator, and you can see it also here, is 1 more than the degree of the denominator. The degree of the numerator is 2. The degree of the denominator is 1. Remember, the degree is just the highest exponent that you're seeing on your variable. So I'll even note that here, where we have f of x is x squared plus 1 over x. The degree of the numerator is 2, and the degree of the denominator is 1. So x squared, x to the first. So the degree of the numerator in this case is 1 more than the degree of the denominator, hence there is a slant asymptote. There is a slant asymptote. Okay, so let me show you how to find the slant asymptote. You're probably going to be mad about this one because when I get done showing you how to find it, it was actually there all along. but it's not always going to be the case. So I want to show you how to find it in general so that you'll know how to find it next time. Okay. Let's do some polynomial long division. I'm trying to think, have we done it in this class, polynomial long division? And I can't remember. Take your function and divide it out. So x squared plus 1. Oh, don't forget, when you're performing polynomial long division in your dividend, you need to account for every power of x. So you don't have an x to the first power, but you need to write it as 0x in your dividend. And you're dividing that by x. All right, so we're going to do polynomial long division. In this case, we're just dividing by a monomial. So you're taking x squared and dividing it by x to get x. X times x is x squared. And then you're going to subtract. And when you subtract, you end up bringing down whatever you have left, which is 0x plus 1. 0x is just nothing. So if you don't want to write it, fine. And then you're going to divide again, and you're going to take 1 divided by x. In that case, you can't divide any further because now the degree in the numerator is less than the degree in the denominator. So you'd be done here. So you're going to add this to your remainder divided by your divisor. And you end up getting that f of x equals x plus 1 over x. And you're kind of like, seriously? You already told us that. Fine. That I'm not always going to give you that. You're not always going to see the function written in that way. That's my point. So I know this time it seemed like it was a trick, but it wasn't. Okay, so if you're wondering, like, how does this help us with the slant asymptote? The slant asymptote is the non-remainder portion of the quotient. Let's see, I don't want to say that. The slant asymptote is y equals the non-remainder portion of the quotient. Here, that means y equals the non-remainder portion is x. The remainder portion is the 1 over x, so we don't include that. Y equals x. This is your slant asymptote. I'm going to show you how to graph that when we graph the function, but it's basically just an asymptote that is on this line, y equals x. So it's not a vertical or horizontal asymptote. It is a slant asymptote, and it follows this function. Okay. Terrific. Wonderful. Now, you know how for some problems, we spend a little bit of time on the algebra, and then there's a ton of time spent just like finding derivatives and stuff. Like I feel like the last example was a little more derivative heavy. With this one, it's just a little bit more algebra heavy. So now that we are beyond the algebra portion, we are ready to find the derivatives. We'll do that next. Right? I feel like I forgot something, but maybe not. I'm going through my mental list. It was domain, intercepts, asymptotes. Yeah, that was 1, 2, and then the derivatives were 3. F prime of x. Well, again, we had f of x written a couple different ways. You know, I'm just going to remind you of f of x before I take the derivative. We had it written like this. If you want to keep it like that, that's going to be easier to take the derivative. We'll just have to rewrite it as a quotient in order to examine it. Kind of up to you. So this will be 1 minus x to the negative second, which is 1 minus 1 over x squared. And if you want to rewrite this as a quotient, that's x squared minus 1 over x squared. And that's f prime. And you know, it's up to you what form you want to keep for entering this in your calculator and evaluating. The second derivative you can use this form for if you find that easiest. So a negative times a negative is a positive. Bring your exponent out front and decrease the exponent by 1, and you just get 2 divided by x cubed. And that's a lot easier than using the quotient rule on this quotient. So I don't know. You play around with the forms, use what's easiest. All right, so for critical numbers, we're looking for places where f prime is equal to 0, and that's going to be where the numerator is equal to 0. So x squared minus 1 is 0. And that's going to be x squared equals 1, and that means that x will be plus or minus 1. So this is where we're going to have relative extrema. Also, we're going to look at places where f prime does not exist, and that would be where x squared equals 0, which means x equals 0. However, if I can remind you, we excluded 0 from the domain because it made your original function undefined. So we're going to say that this is not in the domain of f, hence it can't actually be considered a critical number. And plus, think about it, there's a vertical asymptote there. How come we have a local min or max on a vertical asymptote? Can't be. All right. Points of inflection. F double prime of x equals 0. Well, if that's the case, we would be looking for 2 over x cubed equals 0, and 2 cannot be equal to 0. And then as far as f double prime of x not existing, you would have to have x cubed equals 0, which means x equals 0. Also not in the domain of f. If it's not in the domain of f, it can't be a possible point of inflection. How could it be a point of inflection if it's an asymptote? So you actually have no possible points of inflection. So the only interesting stuff that's really happening on this graph is happening with the slant asymptote and with your local mins and maxes. And that's it. So you have no possible points of inflection. Such is life. Okay, so now that we have that information, we're going to go ahead and set up a table. We're going to have to include that vertical asymptote in the table at x equals 0 that's not included in your domain, and then plus and minus 1. But that's it. Any critical numbers, possible points of inflection, and vertical asymptotes will go in your table. Leave that here. So I'm going to go from negative infinity up to my first interesting value, which happens at -1. Then I'm going to go up to 0. Then I'm going to go from 0 to 1, and then from 1 to infinity. I'm going to pick a test point. I'm going to evaluate f prime, and f double prime at the test point, and then I'm going to make some conclusions regarding the behavior of the graph at those values. Okay. I'm going to test -2, -1/2, +1/2, and +2. I'm having a hard time getting my calculator to show up, so you should be working along with me in your calculator. And we're going to enter these functions. F of x, if all else fails, make sure that you enter this appropriately. You might want to enter it the way that in which it was received, x plus 1 over x. F prime is going to be 1 minus 1 over x squared. And then f double prime is 2 divided by x cubed. So this, because that's really clear, right? This, gosh, you guys, it's like a nightmare. No? Maybe? X plus 1 over x, 1 minus 1 over x squared, and 2 over x cubed. All right. I'm going to enter these values for the test points in my table. Now, I'm not going to bother with x equals 0 because I know that the function is going to be undefined there, and I know that all the derivatives are going to be undefined there. We already said it's a vertical asymptote, so that we don't need to worry about. But I am going to enter -1 and +1 because remember that these were supposed to be local extrema. And if you want to go ahead and list where you found them and what they were supposed to be, that's fine. But if they're extrema, they're points on the graph, and I want to know what the corresponding y value is. So I am going to look at the y values at those points, although I don't need to look at anything else there. So I'm going to enter in my table -2, -1, -0.5, +0.5, 1, 2. So I have these 6 values that I'm checking. All right, I'm going to go through and do f of x first. That's the y sub 1. That's going to be -2.5. Let's see, -2, -2.5. Interesting. At 1/2, we're at 2.5. At 1, we are at 2, and at 2, 2.5. For f prime, that's y sub 2, you're at 0.75, 0, -3, -3, 0, and 0.75. Now remember that f prime is dictating whether your function's increasing or decreasing. You don't have to, but you can use the arrows right now to sort of discuss what's happening with your function. You went from increasing to decreasing, so you have an idea now of what this value is going to represent to you. The first derivative was 0 there. That's why it's an extrema, or it's an extreme value. F double prime, -0.25, -2. I don't even need this value. I have it, so I'm using it. -16, +16, 2, and 0.25. So we are concave down, concave down, concave up, concave up. Now, we didn't have any possible points of inflection, so we weren't looking for that concavity to change. Even though it changed from here to here, it's changing at a vertical asymptote, so it's not really doing anything for us. But we know that we are increasing concave down on the first interval, decreasing concave down on the second, decreasing concave up on the third, and increasing concave up on that last interval. We had local mins and maxes occurring at -1 and 1, so now we can figure out which one was which. We went from increasing to decreasing at -1. So that means that we have a local max at -1, -2. And we went from decreasing to increasing at 1, 2. So So that means we must have a local min at the point 1, 2. So x, f of x. All right. Chart's done. Now we're going to graph the function. Let's see. I'm looking at my table though, trying to figure out how high this graph needs to go. The highest x values, the highest y values I have are at like 2.5. The lowest are at negative 2.5. The extreme values, pretty small. There's really nothing crazy going on here. So again, I might just go out from -4 to +4. You can even just use 3 if you want, but I don't know. I feel like it's easier to graph using even numbers because then you can just split them in half to get your other tick marks. That's just me. Last time I made this too big for it to fit on your screen. So I'm going to try to make it a little smaller this time. X, Y. This will be 4. This will be approximately 4. -4. That's too close. I don't know. -4. Do the best you can. Okay, remember we graphed the asymptotes first. We have 2 asymptotes. We have a vertical asymptote at x equals 0. Don't forget about that. I know that is long forgotten because we got so focused on finding the slant asymptote. But go ahead and put down that vertical asymptote at x equals 0. Make sure I can see it. Now you have a slant asymptote at y equals x, and that's really going to help to shape your graph. Remember, y equals x is that identity function. If x is 4, y is 4. If x is 2, y is 2, so on and so forth. It's just that 45-degree diagonal. So we're going to go like that and get those, points to kind of help us along. And this is your slant asymptote at y equals x. Okay. The other points on your graph are the local mins and maxes. You have a local minimum at 1, 2, which is right here. And you have a local max at -1, -2. If you'd like, you can graph some of these intermediate points that we found in the chart. That's kind of why we evaluated the function there. We have a point at -2, -2.5. So at -2, -2.5. That's -3. This is about -2.5. You have a point right here. And then you have a point at +2, +2.5. Which is about right there. We also had points that we had at 1/2, 2.5, and -0.5, -2.5. So 1/2, 2.5 is about right here. And then -1/2, -2.5. Well, it's this guy that's kind of off. He looks like he's closer to 3. There we go. It's a little better. And these values just came from your chart. But now you can see that your graph has to approach these asymptotes. You know that your local min is at 1, 2. So you know it's going to hit this bottom value and go back up again. So I want you to graph this just kind of showing that the graph is approaching the asymptotes. Show that you have this minimum at 1, 2, and it's just kind of going along its merry way. It's not going to cross the vertical asymptote. It can't do that, but it's going to approach this slant asymptote as it moves up and to the right. And it's going to do this, something very similar in the bottom. So you have this local max at -1, -2, and your graph is going to be approaching the asymptotes, but not touching, something like that. And don't worry too much about finding all the little values in here. I'm not too concerned about it. I mean, it's helpful just to have those extra points that you graph, but really there's only one thing your function can possibly do in here, and it's to hit this maximum and then just approach the asymptotes. And that's how you graph a rational function with a slant asymptote, which is very exciting. Okay. So now we're going to graph a polynomial function. We're moving away from rationals. We're going to graph some polynomials. I can remember being a student in calculus, and this was my favorite section. And I would do all my graphs on this nice pad of graph paper. And it was just so satisfying when you got done and all the information came together and you got this beautiful graph. Oh, I hope that you have that feeling of contentment when you work on your curve sketching problems. I believe that this is example 5. 1, 2, 3, 4, 5. All right, we are looking at f of x equals 4x cubed minus x to the 4th. Now, some of you might find that polynomials can be easier in a lot of ways. Their graphs are a little bit harder to sketch just because of the behavior where you don't have asymptotes. You just got a bunch of flippy behavior going on. You have to be a little bit more careful how you draw your scale for your graph because these polynomials sometimes can increase and decrease very rapidly. However, the derivatives are easier and the domain is all real numbers. So in some ways, there's less to do here with polynomial functions. All right, so we can let x be any real number and we're good to go. Intercepts. To find the x-intercept, let y equals 0. And that is going to happen when your function equals 0. So you have a little bit more work to do here maybe than you would have with a lot of the rational functions. Go ahead and factor out an x cubed, and that leaves you with 4 minus x equals 0, which means x cubed equals 0, and 4 minus x equals 0, which means x equals 0 and x equals 4. So that's kind of nice. You have 2 x-intercepts. A lot of times with these polynomials, you will have multiple x-intercepts. Not always, but a lot of times you will. Okay. And you know what? I'm going to bring you back to this later on when we're talking about graphing these intercepts, to remind you of some algebraic properties. Oh, and by the way, in intercept form, these would be 0, 0, and 4, 0. So those are the points you're going to plot when you graph your function. To find the y-intercept, we're going to let x be 0. So we're looking for f of 0, which is going to be 0. So we already have that point. Oh, well. Got to look for it anyway, even if it's not that interesting. The next thing you're looking for is asymptotes. Polynomial functions don't have asymptotes, but we do need to talk about end behavior. We did talk about end behavior when we were talking about infinite or limits and infinity with these polynomial functions. We need to, first of all, write this in descending order. A lot of times it's just written in the so that the order of subtraction is just right. But we can rewrite f of x as negative x to the fourth plus 4x cubed. Thinking back to, I believe it was section 1.5 when we talked about end behavior, we said that if the degree of your polynomial was even, then the ends were both doing the same thing. Either they were both going up or they were both going down. If your lead coefficient was negative, then they were both going down. If it was positive, they were both going up. So recall, I'll say recall. If n is even and the lead coefficient is negative, then you have a situation where both ends of your graph head down. I mean, whatever happens in between, we don't know. We're going to find out, but this is your end behavior. If n is even and the lead coefficient's positive, then you'll have both ends going up. And in my next example, I believe I have a cubic function. Yeah, so we'll talk about what happens when n is odd in the next example. All right, so this is our end behavior. So it does not matter to me if you write this formally and say, as x approaches infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches negative infinity. I don't care. If you just draw me a little sketch of what you expect your end behavior to be, that's fine. Okay. That's end behavior. All we have to do is take the derivatives now. Gosh, I keep thinking there's something else to do here. F prime of x is going to be 12x squared minus 4x cubed. F double prime of x is going to be 24x minus 12x squared. When we're looking for critical numbers, we're going to take our first derivative and set it equal to 0. So go ahead and take your first derivative and factor out a 4x squared. That leaves you with 3 minus x equals 0. And x equals 0 and x equals 3. To find possible points of inflection, and I'm expecting points of inflection with a polynomial, absolutely. I'm going to do something similar with the second derivative. We're going to go ahead and factor out the common factor, which is 12x. That leaves you with 2 minus x equals 0, which means x equals 0 and x equals 2 are possible points of inflection on your graph. All right, it's chart time. Yeah, it's chart time already. All right, so in your chart, normally we would include any vertical asymptotes. We don't have any here, but we do need to include the critical numbers and the possible points of inflection. So I am going to need to include those here. So I'm going to start out at negative infinity, and I'm going to go up to the first important point that I have. And by the way, 0 is repeated here. So it's possible the inflection changes there. It's possible that we have a minimum or maximum value there. Either way, we need to focus on including 0 in the interval and cutting it off at our first point at 0. And then we'll go up to 2. And then we'll go up to 3. So we're going to look at f of x, f prime of x, f double prime of x, and then we're going to make a conclusion. And you're going to make me a nice chart. Maybe I made my chart too small to work on that. There it is. You are going to enter into your calculator f, f prime, and f double prime. F is 4x cubed minus x to the fourth. F prime is 12x squared minus 4x cubed. And f double prime is 24x minus 12x squared. All right, you're gonna go to your table. I'm gonna enter all of these values. Oh, I didn't put any test values down. Whoops. -1, 1, 2.5, 4. And I'm gonna look at 0, 2, and 3. So I'm gonna put all 7 of these values into my x equals on my table. So -1, 0, 1, 2, 2.5, 3, 4. So I'm gonna do the, I wish there was like a flip a switch on my light where I could somehow make it all happen. Usually the dimmer it is in here, the easier it is to see the screen, but that's not the case. Let me try something. You can't see my pencil if I turn the light above me on. Let's see what happens. Whoa. Holy cow. All right. So that's a little bit better. And actually you can see the pencil better than you could before. I actually started to record you a lecture and I couldn't see the pencil. I was just like, yeah, this is not happening. So I had to stop it and re-record for you. Okay, I wonder what would happen. I don't know. You guys, that's as good as it's going to get. I mean, technically I could zoom in on that for you. Looks better over here, actually. Either way. Oh, the technical difficulties. My y sub 1 column is representing f of x. I'm just going to go through that from left to right. -5, 0, 3, 16, 23.438, 27, 0. And then I'm going to go to y sub 2 for my f prime. 16, 0, 8, 16, 12.5, 0, -64. I'm double checking as I go through because if one of these numbers is wrong, everything's going to be based off that and my graph is going to look very odd and something's going to be wrong and I'm not going to know what it is. Y sub 3, -36, 0, 12, 0, -15, -36, -96. 0, 12, 0, -15. Yes, yes. Okay. Oops. Oh no, we don't want to see the graph. That's like a spoiler. Well, now I have every single light on in this house at like 1:30 in the morning. Ugh. Terrible. Okay. But I feel like this is, like you can see this pretty well with my light on. I'm just going to leave it on. I was also trying to keep the light low. So I just got done with a really long Peloton workout. And I'm just like gross. So I was trying to not be gross on camera. I thought maybe I'll turn my camera off so that if I can't see them, maybe if they don't see me, big deal. But I can't just have a voice teaching to you. I feel like you need to see me, even if it's gross. All right, I'm going to make some conclusions now. All right, I'm looking at these intervals. The derivative is positive, my function's increasing. The derivative's positive, my function's increasing. Interesting, because over here I had 0 as a critical number and a possible point of inflection. The other possible point of inflection was here, and the other critical number was there. So just kind of getting an idea of what I was expecting. I had this critical number, but my function did not change from increasing to decreasing or vice versa. Increasing, decreasing. So we're increasing most of the time and decreasing on that last interval. Concave down, concave up. All right, so that is definitely a point of inflection because I'm seeing the concavity change there. Concave down, concave down. Well, I wasn't expecting the concavity to change here. I was expecting it here at 2, and it did change. So that's clearly going to be a point of inflection for us. So, I mean, since we just talked about it, if you want to go ahead and say, okay, the concavity changed. I was expecting this to be a point of inflection. Clearly, it is a point of inflection. It's happening at 0, f of 0, which is 0, 0. And we also have a point of inflection at 2, 16. As far as our critical numbers are concerned, like we said, we went from increasing to increasing. So we're not expecting that we have any local extrema here. It's not happening. But you can go ahead and just write down what's happening as far as the concavity and the increasing, decreasing situation is concerned. Then we were increasing, concave down, decreasing, concave down. X equals 3 was a critical number, and we went from increasing to decreasing there. So we had that our function was going up and then down. So we have a local max at 327. So you're seeing now that even though like some of the work to get here was a little bit easier, the graph is going to be a little bit more difficult because we're not looking at a situation where now we can just graph from -4 to 4. We're going to have to put a little bit more thought into how we label our axes and how we situate everything. Oh, you guys, like my focus is not as good anymore now, though. Sharper. Maybe that's a little better. Wonderful. Let's go ahead and graph this. I'm looking at maybe the highest y value I'm going to come across here is at the local max at 327. The other x value, the other f of x values I have, I mean, I have 23.438, and then the other one is -5. So nothing else was really happening there. My intercepts are at 0, 0, and 4, 0. No big deal there. So I know x needs to at least go out to 4. But we were going to do that anyway. So here's what I would suggest. I would suggest going at least up to 27, so probably go up to 30. But as far as how far down you go, I mean, -5 is about as far as we need to go. Maybe just go down to -10, just so you can get like a complete picture. And if you'd like, just kind of balance this out a little bit this way. And as far as the x values are concerned, I mean, technically we could have shifted that axis over because more of the graph is appearing on the right-hand side. I don't know, that's up to you. So we said we were going up to 30. If you want to split that by tens, you can. If you find it easier to go in half and then split it that way, that's fine too. That's for your y-axis. And then we said -10 was okay. As far as your x-axis is concerned, everything that's interesting happens between -1 and +4. That's it. So I don't know. Go out to 5, I guess. Call that 5. Oh, I hate when I use 5 because now I have to split this into, see, 1, 2, 3, 4. Close enough. And then maybe -1 will be right there. -2 will be right there. Not that we'll need it, but it's there for us. Okay. All right, so let's go ahead and graph the intercepts first. We have no asymptotes to graph, but I have intercepts at 4, 0, and 0, 0. Those are our x-intercepts. I have a point at 327. That's a very crucial point for us, so I'm going to plot that. I'm going to try to be as careful as I can. I'm going to get close. I mean, obviously, it's not going to be exact. This represents a local max. So you're kind of thinking that, all right, this is the highest point I'm going to obtain for a while. And then if you'd like, you can go back to your table and just think about graphing some of these other values. You could graph your point of inflection at 216. You already have a point at 0, 0, so there's nothing to do there. But if you want to go ahead at 216, which is about right here, and graph that point. And this is a point of inflection, so your concavity is changing here. When you're looking at a polynomial function where there's so much going on, you might want to just label that so you remember that you're supposed to be looking at an inflection change. Otherwise, it might be hard to see. Or you might forget and just kind of swing some sort of curve down there. And then other than that, we had a test point at -1, and then the y value is -5. So let's go ahead and just plot that here. So that's the point at -1, -5. And then our other test points gave us points at 1, 3. And 2.5, 23.438. Do the best you can with that one. So 2.5, and then 23.438. I don't know. Sure. Now I don't have anything between 3 and 4. And that's okay. I don't think we'll need anything. These extra points are helpful, but not completely necessary. Okay, but now we really need to follow our chart. I know that 4 is an x-intercept. The thing I was going to remind you about, you don't have to use it, but if you remember it, you'll find it to be helpful here. Do you remember in college algebra when you were talking about multiplicity and you were looking at x-intercepts, and the multiplicity of the x-intercept would determine the behavior of the graph at the x-intercept. So for instance, when you factor this, this particular factor of x cubed equals 0 gave you the intercept at 0. We would have said, though, that this was multiplicity 3. And then this factor was just to the first power. We technically didn't write the first power, but this factor is multiplicity 1. Odd multiplicity intercepts are going to cross through the x-axis. Even multiplicity intercepts touch and turn. You remember this? Okay. Like a third of you will probably, this will be ringing a bell. And then for the rest of you, you're going to be like, huh? I took algebra how many years ago? I get it. Don't worry. I thought we should bring it back. It is in your prereq technically, and I would hate for you to think that your prereq had nothing to do with what you're doing now. Both of your zeros had odd multiplicities. Therefore, you know that your graph is going to cross through at those x-intercepts. Now, you can kind of see what's happening as it crosses. This one has to be coming from the point 1, 3 to 0, 0 over here to -1, -5. So something like that's happening. You just don't know exactly what. This can't be vertical, but it's clearly like very slowly moving to the right as it heads down. Now this is your local max. You know that's the highest value you're going to obtain. Follow your concavity here. We know from our table, and I'm just going to start at the local max, that before I get to the local max, I'm concave down, and then on the other side of it, I'm also concave down. So I'm expecting to be concave down until I hit this point of inflection at 216. So if I'm going to be concave down, I need to make a frown, not a cup. See how I was starting to make a cup? Not a cup. It's got to be a frown. So I'm going to frown until I get to 216, and then you can see where the cup comes in. So if you want to draw the cup first, be my guest, draw the cup. And over here, concave down, frown. Do the best you can. But we are concave down from 3 to infinity. So this is just going to continue to be this everlasting frown as it works its way down. I also had a point of inflection at 0, 0. So we're concave up in between the 2 points of inflection, concave down on our leftmost interval. So concave up in between these 2 points of inflection and then concave down. So if I know that I'm going to be concave down on the interval from -infinity to 0, then I want to kind of swing this intercept a little bit more, make it a little bit more curved. So this is concave up between the two, and it's kind of like it curves down. And I mean, I don't know how rapidly it goes down. If you want, you can get another value to look at, maybe see what happens to the graph at -2. I mean, it's already in your calculator. So you can already go to the table and just look at what happens at -2. The function value is -48. So that means at -2, I mean, we'd have to go all the way down here. I mean, I wouldn't even be able to fit it on the page because this would be -40. So it's really far down here at -2. So you can tell that this is a pretty steep decline. But there it is. Make sure it's following what your table says. Increasing concave down, point of inflection, increasing concave up, increasing concave down, decreasing concave down. Is this life-changing for anybody? Come on, you guys. Come on. This is super cool. I love this. I just think it's really cool to analyze this information. And also just to pull in these pieces from algebra. Oh, it's very cool. All right. I'm going to do one more polynomial because I feel like these are definitely harder to graph. So students tend to like to see a couple more examples of this, but you're going to get one more polynomial. I mean, the work for them isn't that hard. It's just kind of getting practice actually graphing the functions. Okay. All right, one more polynomial. This is example 6. f of x equals negative 1/3 x cubed plus 3x squared minus 5x. You know what? I should probably just let you know now. I'm looking at the clock and I have no idea what time I actually started, but I feel like I'm at about an hour and a half right now. And I had technically 2 more examples, and the last one was a radical function. I think we'll just finish this polynomial and call it a day, because I really don't want this asynchronous lecture to go on more than 2 hours. Because I know there's going to be time where you're pausing this and trying to catch up. So for you, this could take 3 hours to get through, and that's the last thing I want. So maybe we'll just do this polynomial and we'll skip the radicals. There weren't very many of them in your book anyway, and the examples weren't that great. Not my example. My example was great, but the exercises in the book were just meh. So I'm just going to have you focus on rationals and polynomials. I think that's plenty, 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 plenty. Okay. Domain, it's a polynomial. Its domain is all real numbers. Let's look at the intercepts. To find the x-intercept, we'll let y equals 0. Or f of x equals 0. Those are synonymous. That means we're solving the equation 1/3 x cubed plus 3x squared minus 5x equals 0. This is where you're going to have to do a little bit more algebra with these polynomials. You can factor out an x, that's no big deal, but you probably are going to want to get integer coefficients on this particular equation. So I'm going to multiply both sides by -3. So when I do that, -3 times -1/3 is +1. And then -3, -3. And then you can factor out an x. And it looks like this. And then you're asking yourself, well, what 2 numbers multiply to 15 and add to -9? You're not going to find them because you're going to have to use the quadratic formula. But at least we know that x equals 0 is an x-intercept. That's something, right? Okay. Quadratic formula, x equals -b plus or minus the square root of b squared minus 4ac, all divided by 2a. This is why you want to have integer coefficients. The last thing you want to do is use the quadratic formula with a fraction. I wouldn't say that would be like a nightmare, but it's more work than you need to do. So -b plus or minus the square root of b squared minus 4ac, all divided by 2a. 9 plus or minus the square root of 81 minus 60 equals 9 plus or minus the square root of 21 over 2. Now you're going to have to graph these. That means that this is an occasion where you definitely want to get some sort of decimal approximation. 9 plus the square root of 21. By the way, when you put this in your calculator, make sure that if you do it all at one time, that you put parentheses around the 9 plus the square root of 21. You would be shocked how often students forget the parentheses and then their solution is wrong and they're wondering why, what happened, how come you got that x-intercept and I got something different. Okay, so the plus variation of that gets us to about 6.8. Again, you're going to have to graph this. So don't tell me it's 6.7912878847. You're going to have to graph it. This is more precise than you're going to be able to graph. So it's fine. Pull that back up again, change it to a minus, and you'll get the other one, which is at about 2.20. So you have 3 x-intercepts. This one at 0, 0, and then these 2 that you just found using your quadratic formula. Okay, now asymptotes. Oh no, wait, y-intercept. Almost forgot about that. So we found the x-intercept, I mean the y-intercept. Come on, it's right there. But that's okay. F of 0 is 0. Done. Okay, asymptotes, it's a polynomial. Polynomials don't have asymptotes. So we're going to say none. But end behavior we need to consider. I'm going to rewrite your function just because I can't keep pulling this up. And we need to reference it. For n odd, and n is, of course, the degree of your polynomial, and you have a negative lead coefficient, you're going to have the end behavior doing opposite things anytime n is odd. So if the degree of your polynomial is odd, you're either going to have this happen or this happen. So you can't see this if I turn off my video. And you need to figure out which one's which. If your lead coefficient's negative, then your graph is going to look like it's going down from left to right. So it's going to be kind of like this. And I just leave this dotted because we don't know what's happening in between. We just know that as x approaches negative infinity, f of x approaches infinity. And as x approaches infinity, f of x approaches negative infinity. That's your end behavior. All right, so remember, if n is odd, your end behavior is going to be going 2 separate directions. If your lead coefficient is negative, then your graph is going to sort of look like it's going down from left to right. If it's positive, then you would have the opposite situation where it would look like it's going up from left to right. So that's your end behavior. All right, now we can find the derivative and the second derivative. And then we'll make your chart after we find critical numbers and possible points of inflection. All right, so here's your function, f of x. Negative 1/3 times 3 is negative 1, and then x squared, and we'll have plus 6x minus 5. If you want, sometimes it's just natural to, from here, just set this equal to 0 and solve, and that's fine. If you want to do this first and then find the second derivative, that's fine. I'm going to multiply through by a negative 1 just so I can have a positive lead coefficient on this polynomial expression on the left. And the 2 numbers that multiply to 5 and add to negative 6 are negative 1, negative 5. This is so commonly missed. Students always want to say 2 and 3, or like negative 2 and negative 3, because they just associate 2 and 3 with both 5 and 6. But be careful here. Make sure that your numbers multiply to 5, add to negative 6. X equals 1 and x equals 5 are critical numbers. F double prime of x, don't use this version where we multiplied through by a negative. That we only did that to solve the equation. The actual first derivative is this one, negative x squared plus 6x minus 5. Use that to get to the second derivative, otherwise your signs will be wrong. Negative 2x plus 6. We're looking for possible points of inflection, and you're going to get one at 3. Okay. Let's make our chart here. Remember, we would normally include vertical asymptotes in the chart. We don't have any discontinuities here to worry about. So we're going to use our critical numbers and our possible point of inflection 1, 3, and 5. So I'm going to start at negative infinity. I'm going to go up to 1. I'm going to go from 1 to 3. I'm going to go from 3 to 5. And then I'll go from 5 to infinity. All right. I'm going to pick some test values. I'm going to look at the function value, the value of the derivative, the second derivative, and then I almost used the third derivative. Nope, not doing that. We're going to make some conclusions. I am going to test 0, 2, 4, 6. I know that was very predictable. All right. Remember your critical numbers were 1 and 5. Just, I don't know. I feel like it's helpful to include that so that you remember what you're looking for. It's a possible point of inflection. All right. I'm going to enter into my calculator F, F prime, and F double prime. If I can remember what they were. I have a second too. There we go. So let's see, F is negative 1/3 x cubed plus 3x squared minus 5x. F prime is negative x squared plus 6x minus 5. And then F double prime was negative 2x plus 6. All right, that looks good. I'm going to go to my table. I'm going to put all the values in here. So I'm going to start at 0. I'm going to do 0, 1, 2, 3, 4, 5, 6. And I'm going to write all these down as I work my way through. All right, so y sub 1 is representing f of x. So I have 0, negative 2.3 repeating, negative 0.67-ish, 3, 6.6 repeating, 8.3 repeating, and 6. Y sub 2 will represent the derivative. So negative 5, 0, 3, 4, 3, 0, negative 5. And y sub 3 is representing our second derivative. 6, 4, 2, 0, negative 2, negative 4, negative 6. Notice how I kind of just write my numbers a little bit to the left in the cell, just because I like to kind of know what's happening there as far as whether the function's increasing or decreasing or concave up or concave down. Sometimes I go through and just double check to make sure that everything looks good. If one sign is off or a point is off, my graph's going to go haywire. Okay. Decreasing, increasing, increasing, decreasing. Concave up, concave up, concave down, concave down. Now, my critical number at 1 is representing a local min. I went down and then back up again. That is occurring at 1 and approximately negative 2.3 repeating. That's going to be negative 2 1/3. which is really at 1 negative 7/3. That would be the exact value, but again, you have to graph this value. So you're going to want an approximate value just to graph. But here you were decreasing concave up, and then you were increasing concave up, increasing concave down. And here your point of inflection was at x equals 3. You changed from concave up to concave down. So it must be the case that you have a point of inflection at 3, f of 3, which is 3. And here we went decreasing concave down. So the concavity is down all the time. Increasing to decreasing means you hit a local maximum at 5, 8.3 repeating. That's 5 and then 8 1/3, which is 5 and then 25/3. So again, you're going to have to graph the decimal. That's where it's going to go. All right, now I'm looking at my values. They're not as large as they were on the last graph. The highest value that I'm seeing here is occurring at 5, 8.3. And then my test value, the negative 0.67. Yeah, I mean, give infinity to 1. Yeah, I mean, kind of depends on how far we want to take this, I guess. We might want to get another point on here, but we'll deal with that in a few minutes. So yeah, I mean, maybe we'll go up to 10. 10 should probably do it. It kind of depends on where you actually put your test value, because if we go left of here, our function values are going to get higher. But I'd say maybe we can go up to 10. That's safe. As far as the x values are concerned, I mean, we really don't have anything that's going on in between 0 and 6. Like, that's pretty much it. So maybe I'll go the lowest y value that I can see is like negative 2.3 repeating, which is our local minimum. So maybe we'll do something like this. We'll go out to about 6 or 7, and then maybe we'll go up to 10. Call that 10, sure. And then let's drag this out a little bit further. 6, 3, 1, 2, 4, 5. It's kind of up to you how you want to scale this out. And again, it kind of depends too on what points you actually are going to be plotting. And then maybe this would be like -5. Close anyway. Y, X. -1. Okay, so let's start to plot some points. Don't forget, oh shoot, I forgot about our x-intercepts. But I guess nothing too crazy is happening, but actually I'm really glad I took this out to 7 now, because we have an x-intercept at 6.8. And then 2.2 and 0, 0. So 0, 0, 2.2, and 6.8. So we know our graph is going to cross through the x-axis at those points. Don't forget about your x-intercepts. Holy Toledo. Okay. I don't know if you want to label these subpoints 1, 2, 3, 4. But we know we have a point of inflection at 3, 3. So that's on the graph. I know I have a local min at 1 and -2.3. That's going to be really close to this halfway point. And then you have this point of inflection here at 3, 3. Your local max is at 5 and about 8.3. So 6, 7, 8, 9. So 5 and about 8.3, maybe. Oh, it looks so different on the screen than it does when I'm staring at it. Focus on. This is going to be a local max. Okay, so this is a max. I know it's concave down on the interval, so I'm going to just kind of make a skeleton of what's happening. This is a min, and I know it's concave up on both sides of the interval, so I know it's doing something like this. Well, it has to be, because it has to go through these intercepts. I know that this graph is going to be concave up all the time from negative infinity all the way up to 3. And that's when the inflection changes. So I know that it's going to be concave up cup to this point of inflection. I started to make it concave down. I want to be careful with that. Now, once it hits the point of inflection, it's going to be concave down at that point. And it has to go through this maximum value. I did not actually graph the point at 4, 6.6. So maybe I'll do that. We might find that to be helpful. Since we have it, we might as well graph it. 4, 6.6-ish. And then even though we had this like skeleton piece of the graph, we can kind of get a better idea now of what's happening here. And we know that it's concave down on that interval. So it went from concave up to concave down. We also had a point at 6, 6 that came out of our test point at 6. So something like that is happening. And we know that it's crossing through the x-axis right there. Now, we can't just chop this off here. You know that it is going to be decreasing concave up. If you'd like, it might be helpful to you to see what's happening at -1. So go back to your table and look at -1, and you'll get 8.3 repeating. You might want to plot that. You don't have to, but I think it is going to help to really help get the shape of the curve going on. And this came from your calculator. It was just an extra value. So you know that it's going to come up through this intercept and go through that point. All right, now just verify and make sure that your graph's doing what it's supposed to be doing. From negative infinity all the way up to 1, you are decreasing concave up. You hit a local min here at 1, -2.3. Then you are increasing concave up until you get to 3. At that point, you're increasing concave down from 3 to 5. Hit the local max at 5, and then you're decreasing concave down. Your multiplicities were all 1 for your intercepts. So you're seeing that the behavior of the graph is that it crosses through at all those points. And that's how you graph a polynomial function. I'm going on about 2 hours now. So I'm going to stop. I'm really sorry if you felt like you lost out on that radical function. It wasn't a very hard function to do, but I won't assign any. I will, in the email that I send for this, just give you a couple extra homework problems to do for maybe another slant asymptote problem for rationals and then some polynomials. It's going to take a while for this video to process, but I'll get that out to you. Otherwise, reach out if you have questions. I'm going to see if I can do an office hour Sunday. I don't know exactly what's going on around here. July has been nuts, but I might be able to do that. That's it. Email me if you have questions. And I hope you have a wonderful weekend of curve sketching and calculus and preparing for test 4. 2 more weeks, you guys. And you'll be moving on. All right. Adios. Good night. Good night. I don't know when you're watching this. I should say goodbye.